The paper, How We Ruined the Internet, challenges the long-held assumption that a loosely synchronous point-to-point datagram delivery service can meet all network application needs, including those delivering content and services to a mass audience globally. It highlights how the inability of the networking community to provide a public and affordable mechanism for asynchronous point-to-multipoint applications has led to the development of private overlay infrastructure, such as CDNs and cloud networks, which contradict the open data networking goals of early Internet advocates. The contradiction between these initial goals and the monopolistic commercial imperatives of hypergiant overlay infrastructure operators is identified as a key reason for the negative impact of their most profitable applications and strategies, like social media and targeted advertisement. This dichotomy stems from the prioritization of profit over public interest, leading to a loss of openness and democratization in the Internet. The authors propose reconsidering deeply held assumptions, following the prescription of C.S. Peirce, to resolve this contradiction. This requires re-examining the fundamental principles of network design and implementation, taking into account the evolving needs of users and the broader societal implications of technological advancements. In essence, the paper calls for a shift in focus from purely technical solutions to a more holistic approach that considers both technical feasibility and social responsibility. By doing so, it aims to restore the original vision of the Internet as an open, democratic, and public platform for information exchange and collaboration. The original vision of the Internet as an open data network has diverged from its current state in the information and communication technology (ICT) landscape. The end-to-end paradigm, which aimed to build upon the Internet's foundational principles, led to the creation of a stovepipe communication infrastructure. This infrastructure failed to address fundamental limitations, notably the lack of in-network support for asynchronous point-to-multipoint services. This technical limitation provided opportunities for business models that have resulted in negative social, political, and economic consequences. It is crucial to understand the underlying technical factors that made these strategies necessary, acknowledging the role of corporate greed but focusing on the technical aspects as a primary explanation for the current state. The distinction between the original Internet architecture and the modern web applications environment is clarified through the concepts of Internet and Internet++. These terms highlight the difference between the initial vision of the Internet as an open data network and its current form, shaped by various factors including technological limitations and economic interests. The evolution of the Internet has led to a paradoxical outcome, deviating from its original vision as an open data network, ODN. Initially intended to be open to users, service providers, network providers, and change, the ODN aimed at promoting universal connectivity and competition. However, the Internet has evolved into Internet++, which exhibits properties detrimental to these core values. This deviation may be attributed to certain technical features of the Internet architecture. The concept of a stovepipe in system architecture refers to a collection of services implemented within each level of a layered system architecture, characterized by limited focus and functionality, and containing data that cannot be easily shared with other systems. The early assumptions underlying the Internet architecture may need re-evaluation to regain momentum towards the original goals. Thought leaders in the fields of networking and distributed services argue that no new infrastructure can trade off strong properties such as low latency bounds and high availability. They dismiss the possibility of developing such an infrastructure even as a means to achieve the desirable goal of affordable universal service for the world's entire population. Instead, they advocate for policies like subsidized broadband, which are understood to be insufficient for universal service. These policies conveniently direct large sums of money to the employers and benefactors of those who promote the status quo. In a layered system, stovepipes serve as vertical information conduits or slices that define how different elements communicate with each other, maintaining system integrity and organization. Three fundamental stovepipes in ICT infrastructure architecture are storage, networking, and computation, each with separate physical resources and management subsystems, known as stacks. Interaction between these stacks occurs at the highest level through application interfaces, leading to potential inefficiencies and inflexibilities. A spanning layer, a distinguished set of system elements, partitions the software stack vertically, enabling interoperability among different application implementations. This layer separates applications from lower-level services, allowing them to use different supporting services without requiring changes to the application code. A stovepipe spanning layer is preferred for strict access control and maintaining system integrity. Figures 1 and 2 illustrate the concept. Figure 1 depicts the processing, storage, and connectivity stovepipes at the base of the distributed application services stack, while Figure 2 highlights the role of the spanning layer in enabling interoperability and partitioning the software stack vertically. In this layered system, stovepipes and spanning layers are crucial for maintaining system integrity and enabling application interoperability. By understanding the structure and organization of these elements, system designers can optimize system performance and scalability. In digital systems, stovepipe spanning layers are designed to encapsulate and standardize specific functionalities, but they often result in inflexibility and inefficiency when combined with other resources. The Internet Protocol Suite, for instance, defines a simple datagram forwarding service that encapsulates data transfer, persistence, and processing resources. However, this encapsulation can lead to difficulties for users attempting to integrate this standard with other necessary resources. The adoption of stovepipe spanning layers as community standards can have significant consequences. When imposed on the infrastructure that supports distributed systems, such as the Internet, these standards can lead to issues. Application requirements ultimately determine the resources needed, and how implementers access these resources influences the structure of the supporting infrastructure. The economic or policy power of standard setters versus application communities plays a crucial role in the success of standard enforcement. If standard setters hold more power, standards may be enforced successfully. However, if application communities gain the upper hand, as seen in the case of Internet++, standards that restrict them will be bypassed or disregarded. The Internet Hourglass Stack, with the Internet Protocol spanning layer at its waist, emphasizes the importance of this standard in defining and exporting a simple datagram forwarding service. This visual representation reinforces the concept of stovepipe spanning layers and their role in digital systems. In digital systems, it is essential to consider the potential drawbacks of stovepipe spanning layers, highlighting the need for flexibility and adaptability in standards to accommodate diverse application requirements effectively. The original Internet, referred to as Internet, has several limitations that have led to its evolution into Internet++. One of the primary constraints is the lack of distributed storage and processing services, which are essential for modern applications. To address this, Internet++ employs layering violations and private infrastructure. However, these solutions can result in systems with limited interoperability or the creation of non-shared infrastructure to support specific applications. Moreover, many applications are asynchronous in nature, meaning they do not require real-time communication. This disconnect between the synchronous nature of the original Internet and the asynchronous nature of many applications has been a driving force behind the Internet's evolution. Understanding these requirements is crucial to appreciating the forces that have shaped the development of the Internet. The evolution from Internet to Internet++ reflects the need for more flexible and adaptable systems capable of handling distributed storage and processing, as well as supporting asynchronous applications. In summary, the limitations of the original Internet, including the lack of distributed storage and processing services and the asynchronous nature of many applications, have led to the development of Internet++. This new iteration utilizes layering violations and private infrastructure to overcome these constraints, resulting in systems with varying levels of interoperability and specialized infrastructure. The importance of understanding these requirements cannot be overstated, as they have significantly influenced the evolution of the Internet. The current Internet architecture, built on point-to-point datagram delivery, is ill-equipped to support large-scale asynchronous point-to-multipoint applications. The iterated unicast method, which breaks down point-to-multipoint data delivery into two phases, introduces significant inefficiencies. This approach leads to resource exhaustion and poor responsiveness, particularly when handling large files and high client demand. The limitations of IP multicast, including its synchronous nature and lack of error correction, further underscore the need for a more suitable solution. IP multicast's synchronous nature restricts its ability to adapt to varying network conditions, while its lack of error correction mechanisms makes it prone to data loss and corruption. A potential solution lies in managing persistent data state within the network. This approach could mitigate the issues associated with point-to-multipoint data delivery. However, it conflicts with the fast path optimizations required for unicast data forwarding at scale. These optimizations prioritize high-speed data transmission over data reliability and accuracy, making them incompatible with persistent data state management. To address these challenges, a novel solution is needed that balances the requirements of point-to-multipoint data delivery with the need for efficient and reliable data transmission. The content distribution problem in a computer network involves M servers and N clients connected through an intermediate node graph, aiming to store files on server nodes and deliver them to clients upon request. Directed at a single server, this can cause network and processing resource overload, known as a hotspot. Efficient solutions involve passing files over a tree structure, reducing total traffic to N and bounding server load by a constant. To mitigate server and network overload without constructing a distribution tree, distributed unicast is employed, replicating the input file on M servers and distributing load evenly, thus reducing the local load on each server by a factor of 1 per meter. Content delivery networks, CDNs, distribute files efficiently across their own servers and use distributed unicast to reach clients, resulting in average server load proportional to the number of servers and total unicast traffic proportional to NP, where P is the average path length from a CDN node to a client. The number of servers deployed by one of the largest global CDNs has increased, keeping the number of servers roughly proportional to the total volume of data delivered to clients and limiting the load per server. The ratio of server nodes deployed to support global total traffic has remained roughly constant in recent years. The Internet initially presented itself as a promising foundation for the Open Data Network, ODN, leveraging its global scalability and demonstrated ability to facilitate international communication and publication. However, as the network of networks expanded, the limitations of the Internet's core service became apparent. The need for asynchronous point-to-multipoint services led to the emergence of content delivery networks, CDNs, and cloud services, which repurposed Internet support infrastructure. Internally, efforts to scale up distributed unicast necessitated router optimizations that ultimately ossified the Internet at the internetworking layer. This has led to the development of workarounds such as FTP mirroring, which evolved into CDNs and cloud services with their own global topologies and policy mechanisms. These alternative networks have transformed from being viewed as applications of networking to being recognized as separate networks with distinct architectures. The evolution of content delivery networks, CDNs, has led to their emergence as new centers of power in the distributed environment. These networks play a crucial role in optimizing network traffic and server load by routing data through them. This process involves leveraging the Internet Domain Name Service, DNS, to access and control the underlying network topology. In the early stages, CDNs utilized policy-based server selection for data routing. However, they eventually adopted a non-standard modification of DNS behavior to choose IP addresses based on topological accuracy. This shift allowed CDNs to better manage data flow and improve performance. Modern CDNs have further advanced their capabilities by accessing internal BGP topology information and shaping the topology through contractual arrangements with Internet service providers. This enhanced control over network traffic enables CDNs to optimize content delivery more effectively. Despite the efficiency offered by tree-based communication, distributed unicast remains prevalent due to its simplicity and ubiquitous deployment. However, this approach has limitations, particularly in terms of scalability and resource utilization. The failure to deploy a shared solution to the content delivery problem has resulted in the growth of a private infrastructure that rivals the Internet communication infrastructure in size and economic power. This private infrastructure, dominated by CDNs, now holds significant influence over how data is distributed and accessed online. In conclusion, the development of CDNs has transformed the landscape of content delivery, introducing new centers of power that shape the flow of information across the Internet. As these networks continue to evolve, their impact on the global digital ecosystem will only continue to grow. Managing stored data and efficiently distributing content over the Internet poses significant challenges, largely due to the limitations of the current Internet architecture. One crucial solution lies in hardware acceleration for datagram forwarding, which enables high performance levels. The concept of a fast path is essential in handling excess traffic generated by distributed unicast, a critical consideration in modern content distribution. The emergence of new applications, such as immersive telepresence, further exacerbates the issue, placing unprecedented demands on backbone routers. To support these applications, a statistically synchronous network is required, ensuring that data transmission and reception occur in tandem. The hourglass theorem highlights the trade-off between strengthening communication services and widening the digital divide. As the Internet evolves to support a broader public, the focus shifts towards accommodating less capable wireless connectivity, particularly through mobile phones. This underscores the need for innovative solutions that balance performance with accessibility. Ultimately, the efficient management of stored data and content distribution rely on the harmonious integration of advanced technologies, including hardware acceleration, fast path architectures, and statistically synchronous networks. As the Internet continues to adapt to emerging applications and user needs, it is crucial to address the challenges and limitations of the current architecture, ensuring that the benefits of technological advancements are equitably distributed. The surge in demand for low-latency communication networks, driven by the popularity of telepresence and real-time streaming services, has led to increased connectivity costs for end users. This commercial imperative to support real-time streaming and telepresence is primarily subsidized by large corporations and wealthy nations, resulting in high costs, network instability, and compromised universal access. In contrast, large application vendors like Netflix have developed strategies to support their most profitable user communities by leveraging buffering outside the network and edge resources, reducing the demand on real-time connectivity. This approach allows for looser bounds on delay and loss, making it more feasible to support critical applications for users who cannot afford high bandwidth, low-latency connections. The evolution of content delivery networks, CDNs, and cloud infrastructure has been driven by the need to support asynchronous point-to-multipoint services and content distribution. Companies such as Akamai, Google, Amazon, Facebook, and Apple have invested in private distributed storage and processing resources to support these demands, creating a new paradigm for application creation and deployment. However, this private infrastructure is not designed to support all applications, particularly those that do not generate significant revenue streams. As a result, the needs of profitable applications are prioritized, leaving critical services for marginalized communities unsupported. The internal distribution of content to CDN servers is under the control of content vendors or their business partners, and must be supported by their business model, further exacerbating the issue. Ultimately, the build-out of private CDN and cloud infrastructure has resulted in a situation where profitable applications drive the development of Internet infrastructure, while critical services for marginalized communities are left behind. The original vision of an open data network, ODN, in the context of Internet++ has been compromised. The commitment to universal network connectivity is contradicted by the reality of a broadband requirement for low latency, making it difficult, expensive, and unlikely to achieve. Similarly, while ODN was intended to be open to service providers and network providers, the process of supplying an application or service with access to Internet++ now requires deploying numerous CDN replica servers or cloud data centers throughout the network. This path is restricted to information and service providers who can pay their fees and obey the rules of the Internet++ hypergiants. Consequently, the emergence of a cartel of these hypergiants has led to concentrated control over application provisioning. Moreover, the original goal of ODN being open to change, including the introduction of new transmission, switching, and control technologies, has also been thwarted. Despite the passage of 25 years, the functions performed at the Internet layer of the protocol stack remain unchanged. This is evident in the failed traction of technologies such as IP mobility, multicast, and IP security, IPsec, in the public Internet. As a result, The IP network has been assimilated by Internet++ and ossified by the need to support iterated unicast. This has precluded the introduction of new approaches to network connectivity, such as asynchronous point-to-multipoint data delivery, and in-network storage and processing. The paper delves into the transformation of the Internet into the Internet++ and its consequences on the core principles of open data networking. Despite its success in delivering a wide range of applications, the Internet++ compromises key principles such as openness, neutrality, and global connectivity due to the limitations of point-to-point datagram forwarding. The authors argue that these issues arise from the network research community's failure to address the shortcomings of the Internet and instead opting for costly workarounds that primarily benefit commercial interests or government entities. This paper emphasizes the need for a path forward that recovers the fundamental values of open data networking, underscoring the importance of the network research community taking responsibility for its role in perpetuating the current situation. It also pursuing friction-free wide-area ICT and human-seeming AI demands careful consideration of their limitations and potential consequences. The development of such technologies raises critical questions about responsible innovation and the duties of scientists and engineers. Drawing parallels with the concept that the U.S. Constitution is not a suicide pact, it is essential to acknowledge the potential risks and unintended outcomes of these advancements. Unfettered pursuit of technological progress can have far-reaching, detrimental effects on humanity. It is crucial to recognize that scientists and engineers have a moral obligation to develop technologies that align with human values and promote the greater good. This requires a nuanced understanding of the complex interplay between technology, society, and ethics. Ultimately, the responsible development of friction-free wide-area ICT and human-seeming AI hinges on a deep appreciation for the potential consequences of these technologies. By acknowledging the limitations and potential risks, scientists and engineers can work towards creating innovations that benefit humanity, rather than harm it. The impact of smartphone penetration on global communication and networking is profound. Widespread adoption has significantly influenced how people interact and access information. According to Wikipedia's list of countries by smartphone penetration, there is a comprehensive overview of the global distribution of smartphone users. This widespread use has not only changed personal interactions but also reshaped business strategies, public health initiatives, and educational systems. The paper emphasizes that the rapid growth in smartphone penetration has led to increased internet access, which in turn has boosted economic growth, improved healthcare outcomes, and enhanced educational opportunities. Smartphones have become an essential tool for communication, with social media platforms playing a pivotal role in shaping public discourse and social norms. Moreover, smartphones have revolutionized the way businesses operate, enabling e-commerce, remote work, and digital marketing. In the healthcare sector, smartphones facilitate telemedicine, health monitoring apps, and access to health information. Similarly, in education, smartphones have made online learning more accessible, allowing students to engage with educational content anywhere, anytime. However, the paper also notes the challenges associated with high smartphone penetration, such as privacy concerns, cybercrime, and addiction. Furthermore, the digital divide between those who have access to smartphones and those who do not could exacerbate existing social inequalities. In conclusion, the paper underscores the transformative power of smartphones in reshaping global communication and networking. While there are challenges to be addressed, the benefits of smartphone penetration far outweigh the drawbacks, paving the way for a more connected, informed, and digitally savvy world.